Yeah, it's this is the topic, which is, let's say that there's some mechanism for establishing some sort of fund for this, right? What is the ideal chip for Web3, right? So today we have a slide deck, right? Tina is my co-founder, and there's a slide deck on there. And yes, every crypto company needs a Chinese woman called Tina. Or a real crypto Twitter tweet that someone posted at some point. But yeah, what is the ideal chip for Web3 is kind of the motivating question for Fabric. And our first chip has ZK, it has FHE. We're about to show you what we already did. But this is a question about the second chip. We chose ZK as an entry point into confidential computing and trustworthy, let's say, or trustless computing, depending on what kind of branding you want to do. And really, like, that was the intent of that wasn't that necessarily this thing and this thing alone is going to be the end game. Here at Fabric, we believe that all of cryptography, all of the confidential computing, is ultimately going to be the end game, and these are just tools in your tool belt, and you're going to use a combination of them, right? And so our next chip is probably going to have ZK, FHE, and TEs of some sort. And so, how these interact, how these combine, how new functionality can come from combinations of these things, maybe layered on top of each other, maybe used together in some creative way. What other physical features? I think there was an interesting term that Sullivan used, which was cryptophysics. Yeah. We want to go into the cryptophysical realm, right? And so all of those ideas are really the motivating topic for this discussion. So this is less of a presentation and more of a discussion, I think. So we'll talk about what we've done so far for a few brief moments. But then I want to open the floor to most of the time, just talk about questions and really ask you guys, what would the ideal chip be? So yeah, we're gonna start from the VPU V1. The VPU is the verifiable processing unit, right? So the intent for the VPU is basically to be a high-performance processor for things that were too slow before in the domain of cryptography, right? So our first application is real-time ZK proving, and you can run the end-to-end prover on chip. So we actually already have a RISC-V on the chip. We can do everything from witness generation to the proof coming out on chip. It's general purpose, so we did not hard code NTT, we didn't hard code hashes, MSMs, we didn't hard code any of that. It's basically architected like a GPU, right? And it's super easy to program, and it's scalable. So we're going to produce thousands of these next year. They're going to be shipping starting at the beginning of the year in volume to data centers all across the world. And so Fabrica is basically a team of 60, founded last year. We're going in hyperspeed, and we're building VPU V1 with the intent that it's basically, after GPUs have come out for cryptography, FPGAs, ASICs, I think we all have this notion from the last 10 years in crypto that there's an inherent trade-off between programmability and performance. The VPU is intended to break that trade-off. Right? So we believe that you can create a chip that's both ASIC level performance, but also programmable like a GPU. And so there are dozens of supported primitives in this first chip. They all have to do with number theory and big integers. I think Tina came up with a fun catchphrase. I like big ends and I cannot lie. So that's how we feel about it. So it has about 10 times the big N hops as the GPU. And there's an onboard RISC-V CPU that in the next edition may have a TE in it. And there's a CPU to VPU interconnect on chip. Right? So hint, hint, there are a lot of applications for TEs in these cases. And inside the tile is basically a massive number theory vector processor. Right? So think AVX512 for those of you who know vector extensions. It's basically like AVX512 except 1536 wide and a lot of number theory. So that's what the VPU tile is. And so you got a bunch of them in each chip. They can do a bunch of stuff, and the same things that are done for ZK can be reused for FHE. And what we do is basically we focus all of the die area on cryptography functionality. So instead of doing all these AI things, floating point things, we focus the entire thing on cryptography. And so this is a overall die floor plan almost, right? So you have like this RISC-V core complex, you have 40 tile, custom compute instruction set implementation, and then you have these 5 channels of GDDR and a piece of AE. And basically you shrink things like this snippet of assembly to very, very short modular vector arithmetic. And so, as one example, I was presenting this yesterday at the FHE Summit. You get an order of magnitude or more on VPU versus FPGA, so that's a pretty massive improvement. This is on the Zama TFHE UX64 multiplication. Obviously, still a little bit expensive, but you can start to use this kind of stuff if you have a bunch of them for things like auctions.
Also, this is just our FHE.
Yeah.
We can talk about ZK too.
This is a reuse of the FHE deck. So ZK, we get similar kind of cost performance improvements on things like snarks, starks, Quanti 2, Quanti 3, all sorts of amazing things happening.
The cost is just electricity.
This cost is measured as CapEx plus OpEx. So there's like a whole thing about the methodology for measuring that. And then, the flexibility that you have for switching between all these different ZK algorithms basically cross applies to FHE. Right? So I think you guys kind of get the idea, right? Like,
Pulling up your phone and sadly putting it down.
but basically, optimizations are measured in percentages, right? So if you're like a typical ZK FHE software engineer, you're happy if you get like 30%, 50% at a time, and the VPU is designed for a quantum leap, so to speak, a 10x, 20x kind of leap in performance. So some of you might be thinking, okay, so to use this for FHE, you probably need a next gen, to get the truly like several orders of magnitude levels of performance. That next gen is what we're here to talk about today. Let's see what else. Yeah, but this is the first one, and it's shipping at scale. So this is an actual picture of the PCIe card. So any questions before we jump into this? Which is this?
As you're manufacturing these, since a lot of these are going for FHE, security, that kind of thing, is there anything in the manufacturing process that is like unique or that you're doing, such as like what a government would do to make sure that there's nothing along the way you mess with, or like random sampling, stuff like that?
I think that's a next gen thing. Because the current generation is meant for a lot of like these ZK succinct applications that don't really require zero knowledge, but are just like basically centralized or decentralized massive roll-up processing, which is how we got off the ground basically, is like all these roll-ups. And we think that that's a really, really big deal. Like we think that real-time ZK is going to actually make these roll-ups very, very practical. And so like that's kind of the first gen. And the next gen, will continue to have that value prop for crypto. But also we're looking at like a lot of different applications, maybe in the sequencer space, the block building space, so that's like an active area. Yeah.
Can I answer that?
Yeah.
Yeah, the general purpose CPU and the TEE and the integrated GPU, I guess we can implement that.
At that point, you have everything.
Okay.
Yeah. I mean, I guess let's hone in on this question a little bit, which is what makes for a crypto-native TEE. This is really, a huge question that I came in with is like, what kind of technical implementation level details are required for a TEE that truly meets the needs of the blockchain database, right? Like that does a lot better than something like SGX, TPS, and those things, right? So I guess like anyone with a thought on that.
I want to hear your thoughts on tamper resistance, first of all. I mean, so a puff has still been presented as like the necessary but not sufficient for what we need, because that just does its thing of having a secure key and being able to generate images of the key, like signing. We want whole execution, that's unpuffable, untamperable, so that's the problem. You build a whole GPU out of puff, that would solve the tamper resistance.
So the question is, can you build tamper resistance into the logic itself?
Yeah, basically. Yeah.
I think that, so there's a question of like, what kind of tamper resistance are you looking for? Are you looking for like, you literally can't rewire it? Because it's almost impossible to rewire these chips already. Like, in order to break open the chip to the point where you could rewire it, you're already destroying the chip to the point where you can't rewire it. It's like if you redeposit in the semiconductor world above like a sanded down chip, like most likely you've destroyed it to the point. I mean, you could potentially do it, but it would be a very obvious effort. Like you would have to build an entire semiconductor fab. And
What about basically eavesdrop? I mean, the goal is to get out the private keys, for example,
as it runs.
I mean, and to make it harder on us, because you want the ideal design here, even just getting like bits of sensitive information out of it while it runs. But assuming that you have all the time in the world and physical coding stuff.
Yeah. So there's kind of two ways to eavesdrop on a chip, right? The first is, let's say like, keep the chip intact, but basically have wires in to some hidden pads on the chip or something like that. But then the pads would have been inserted at that time. So like I don't think that this will happen if like you have people randomly sampling chips and stuff like that. Like so let's say random sampling quick catch. But then this one is just an EM side channel, right? And I think like this one is probably most preventable with software level tweaks combined with, you know, a lot of like white hat EM attempts. Like I think this one you can only really guard against that way. I mean like you can try to make it a Faraday cage and stuff like that too. Like, you can definitely do that. Maybe that's also a random sampling thing. And then tamper resistance on the package level. So you have the silicon, but usually you have a package on top. And you can put a little like vial here such that the moment that you open the package, this acid will like corrode the chip. So this is another thing that you can do on the manufacturing level. This is like what government people do to protect chips against hostile jurisdiction.
Is that all those? How much are we looking at?
This one is actually a relatively simple one. I think it's a specialty package manufacturer. These things are just random sampling, so we can probably use it.
The other way I've seen it, because Grid Plus, like a hardware wallet company, does this with their hardware wallet. There's like a secure mesh that has like an electron current running through it, if that's active.
Oh, you can totally do that
You can
too.
do that too.
Yeah.
Is it cheaper than the whatever you said, the poison? What did you say? The
Cyanide.
Yeah, that's chips.
Just keep the two.
Yeah, because is that like which one is like has anyone done the chip one with the secure mesh?
I think people have done this one for sure that I'm familiar with. This is a great idea. I think like you can do that.
I think you said you were shaking your head, so is it
Yes,
likely?
secure meshes are like totally industry standard
Okay.
for secure chips. But I would start like way lower with tamper resistance. I mean, this is already like super invasive attacks, which are anyway hard to do with equipment. But currently we don't even have like security against like the simplest kind of side channel attacks that a physical attacker can perform. If I plug my oscilloscope to like an Intel chip, I can get you the key and I can tell you what the enclave is computing at the moment. These are like the basic level things that you need to do. And fault resistance is also a thing that you need to consider at the design level. And we have provably secure design techniques against these kind of attacks. So like tamper resistance, I would start with like the attacks which are cheap to perform, and then move to like the ultra invasive things with like scanning electron microscopes and focused ion beams and changing wires on the chip somewhere. This is like the first thing, but to go into another direction, I think we need tamper resistance and we need open source for trust and decentralization. I know that's kind of an unfair question to ask a commercial company because you need to earn money. But open sourceness to me is like, that's what we need to have in the root of trust, otherwise I'm not willing to trust.
So then there's a question of like, basically, how do you make open source incentive aligned? And I think that's a great question. You know, I think there are some interesting approaches being tried in the AI space, for example. And in the chip world, there might be some sort of equivalent of that where, you know, maybe part of the chip has some logic, right? And this logic could be obfuscated in some way. And then maybe you have a RISC-V, you know, processor, and this part is open source. So your actual acceleration, you know, which is like the ZK FET part, like that could be more closed source, and then maybe this thing.
Yeah, so the ways I've seen it done for, I'm not a hardware person, but how I've looked into this before. So basically, for like, you can make it completely open source, so like Trezor hardware wallets so that everyone copies it. But at the end of the day, people generally will go back to Trezor as the more trusted one if they do a good global approach. There's actually three ways. The second way is kind of what WorldCoin's doing. So WorldCoin has open sourced all their chips, but they kind of waited until they could, you know, get the leg up on production for the most part. And then the last way is what Apple does, I believe, with their chips, where you have parts of it open source, and then the rest you get independent people that are very high trust to say, we've looked at this and it's safe. And then you basically have these certifications that they're starting to come out with. So you would just have someone, you have like people from the crypto community like be like, yeah, like as close as we can get to being open source, we've had 30 people look at this, it's trustworthy.
Yep, that's true. Although there's also a question of, okay, let's say I have some Verilog, and I've shown you this Verilog and it's open source and everyone can, you know, build on it, etc. And then I built this Verilog into a chip, but how do you know that the Verilog corresponds to the chip?
I borrowed the oscilloscope from Dean's Nightmare Fuel for like being able to get anything.
But there are billions of wires on it.
Oh yeah, so like you would just have it checked often and maybe randomized. So basically like
Right.
you have like from the supply line we'd have someone walk up and actually take it and be like, I am checking this, and then like letting you get into it. Same with the code, like there's probably ways to distribute that in open source code levels to kind of get like a Git script or something where it's like at some random point, whatever the next commit is that we decide is grabbed and then taken away from or sent to somewhere else that you can't stop the process.
Actually, this one has a solution from the fab world, which is if you trust the ATE manufacturer, then you know you could potentially have the ATE equipment throw like all the JTAG ports that you left for DFT, and then you would basically do some sort of like interactive proof of like logical equivalence, right? Which is already like kind of what you do, but this would be more costly because you could like have more coverage of like various things.
Just gotta wait 20 years for ZK to be good enough to prove that.
I don't think you have to wait 20 years necessarily.
True.
I think with like maybe 2 generations from now, or 1 generation from now, you'll have like pretty, I mean, you won't have within an order of magnitude to plain text, but like somewhere close. I think it's possible. Yeah.
What potential impacts do you see if you embed those changes in the next gen of your current chips? What are the potential side effects regarding, let's say, performance or
I don't think that it should create that much more performance impact. Like this one, you know, DFT, design for test, is already something that you do for chips. Like it blows up area and like slows down certain things, but it's something you already do, so it's not like you're creating that much more overhead. The random sampling is more of a cost overhead per chip. But again, the chip is like a portion of your overall supply chain. And so the chip may only be a certain amount of cost, right? So if you even double the cost of the chip, it'll create less than a doubling of the cost of the entire unit. So this may not actually be a big deal. And open source, I mean, that's mainly a business question and business implication. And the puff, puffs are pretty small. So like, all of these, I mean, the biggest thing that I can think of is if you're actually making a modification to the RISC object, for example, you're creating some sort of Merkle commitment to memory or something like that. That would be where like maybe an implication would come in. But like this part can actually use super high speed hashing. So like we have like 40 gigahashes of Merkle check per card per second. And so like you could just, transfer some stuff over here and then get a bunch of Merkle chips. Like even so actually like the main expense here is not on the actual like marginal cost. It's on the initial effort to like integrate all this stuff. Like this is all like difficult to set up, but then easy to implement. Yeah, someone.
Yeah, I wanted to ask about why chain attack? Like
Yeah.
Intel provides.
This is a great question.
Intel provides an SDK for Jack, right? And like, how do we forward for the chip in a secure way? What is it?
You're saying, let's say I include your SDK. How do I know that this?
No, I'm saying like, do you provide an SDK? Or,
Yes.
Yes.
We do.
Okay.
How do we protect against the software supply chain?
Yeah.
I mean, that's a great question. I mean, that is like an active conversation that all of us should have. Like, I think that there are plenty of unsolved problems in that kind of first stage. Like, you're not going to be able to seal off the entire security envelope with like one fell swoop. I think it's more of a question of like how many additional layers of security can we put in, how many things can we mitigate with the next one and the next one. So it's going to be an iterative process. I think the problem that you just posed is a problem across the industry, and we kind of don't know exactly what we're doing. Yeah.
So just a quick question, not related to this thing. How do you think about, like in TEEs, we basically have encrypted memory, right? And like some kind of certificate or got a key that there is encrypted the memory flight so that none of the secrets fall out, right? And that's because we don't have FHE.
Yeah.
So do you think FHE will be, a million times faster? And do you just always FHE, or do you want to consider providing something like encrypted memory?
Well, I think on the same process node, FHE is always going to be more expensive than the plain text. That's like, there's no way around it, right? It's always going to be more expensive. The question is how much. I think that something like 10,000x is very, very doable, given enough time, money, etc. The money could be quite astronomical for that, but you can do it. Like, you can do some back of the envelope calculations and be like, you can certainly fit that many gates in 2 nanometer. And then it's just a question of willingness. You have to build a team of hundreds and actually go do it, over a period of years and hire all the people. So, but that's
To be 10,000 times slower than ClearJack, or 10,000 times faster.
faster than the C programs. You can certainly. But the question is a million. A million is like a harder problem. I think the other thing that you can do is you can parallelize it more, and then you can have the cost come within like maybe like several orders of magnitude of plain text. But then the latency could be even better, and then you just parallelize over more machines. Like that's another way that you could kind of compensate for that. Is you're just willing to pay more. Maybe through some sort of like blockchain subsidy of this thing, like you could easily, get rid of this problem. Right? Because if you look at the Bitcoin network, Bitcoin has incentivized SHA-256 to such an extent, we're almost at a zeta hash per second, right? So this overhead, we can figure out ways for everyone to like be able to create something that's positive sum that actually captures.
When FHE rollups?
Sorry?
When FHE rollups?
I think that's more a question for the rollups.
I with Polygon Labs. I don't know. We
Sigh, so
like, it's not about what I want or what you want, it's about what's gonna keep us going for a little bit.
I do
soon.
think the FHE big problem is the MPC on top of FHE. Because we need MPC to distribute the master key. But under the hood there are like just the 10 nodes hosting the key in the threshold network. Compared with like even Tron, it has less nodes.
But it's better than blind nodes, right?
No, of course.
But you're saying we need an incentivization mechanism for those nodes to create more nodes, right? Why is there only 10?
Because the latency and bandwidth requirement grow like all n squared. So far, like the lead network, they only have 10 nodes.
Okay.
Can you get use TEs instead of
Oh, they are already
SE
using
or-
T. They are using AMD SE.
Interesting.
I think one question is like, why can't everything on just a chip? Can you put all this together really powerful, like separate pieces of hardware?
Oh, that's a good question. So
Why do an SoC like system on a chip?
So the question was like, why do everything on one chip? And the answer is like, because there's really high bandwidth between different parts of the same chip. So like, there are kind of, I think someone was pointing out that like, oh, if you have like two bidders in a negotiation, like on a single chip, like that's a really good situation. Like that kind of co-location is the same reason that you want to like put things on the same chip. So it makes a lot of sense to create like a unified Web3 chip, because otherwise you run into a lot of I/O problems. Like for example, a lot of people do like fixed function ZK ASICs, but then the Xeon sending witness data to the ZK ASIC is like super slow. So no matter how fast your ASIC gets, like this is super slow.
I was wondering for the T things there, like all kinds of use cases in a way that where T is a little bit low. Where you can have like specialized secret hardware. So you just need to do signatures, right? Or if you need to do proof of deletion or one-time signatures.
Yeah,
So-
this is a really good question. So I think that like, you know, potentially you have like a secure TE with like a RISC-V, and then you have some other blocks that have different trust assumptions. And basically the goal would be to give people as wide and a diverse a range of trust assumptions as possible. So for example, like I saw a paper somewhere that was talking about like only having a secure multiplier. And I thought, wow, what a great idea, because like all you have to do is trust this one tiny thing that you can test very easily, like in a random sampling context, you can easily test that one multiplier, know that nothing is wrong, right? So like maybe malt, and then maybe like a simple like VM, like you can have all of these, right? You can have all of the above, and then like they all have their like separate, literally physically isolated like sections with like a very secure boundary between them. Like if you can do something like this, then you could potentially leave it up to the users.
Okay. Because this is Torben who's here in this group, they basically know how they could build an open source signing oracle, right? To just sign. So where the private key is secure, even if the device is in the hands of an attacker. But the problem with this is that, right, we don't have a T yet, right? That will be a first step, but the question that can be interesting here is that if that can be a product on its own, or if you can have other kind of somewhat similar specialized minimalistic devices that you can sell that people buy, you know, then it can help also for the ongoing funding effort towards a full-blown team. So that's
Yeah. Well, the great thing is we're already going to come up with the next chip, right? So then the marginal effort to like include these things is still quite high, right? But it's like doable. It's within the realm of reason, let's say.
okay.
So then like you can fit it into the next chip, and then you get all this other functionality, quote unquote, for free, right? You still have to pay for the hardware and stuff like that, right? But like all of it coming in like a one-stop shop is the kind of nice thing. Yep.
Have you thought about chips outside of server racks? Like maybe in a consumer device or
Oh yeah. Yes, I think the end game is that this stuff is going to be everywhere, right? So some subset of what we call the VPU today is going to be hopefully in every cell phone, et cetera. Now, not all of it will have the same functionality, right? Like cell phone, I heard someone say, like someone proposed putting FHE on the cell phone. This is not a good idea. But, you know, there are all sorts of good ideas that, you know, maybe a subset of like the instruction set, or like maybe the entire instruction set of like a few tiles, like as long as you can get the thing off the ground initially, then you can like actually write your entire chip Verilog in a modular way and like be able to make all these different product lines for different contexts. So that's certainly something that we would be interested in.
Did you launch a token yet?
I'll
buy.
We are a hardware company. Sometimes I look around and I regret it. Physical token.
Bad physical points.
Yeah, maybe every chip has its own NFT or something.
That's a good idea. So each NFT is like a attestation to the.
Yeah, like attestation
Very
NFTs.
awesome.
So if anyone wants to contribute, collaborate, has an idea of like how to make this real, right? Like certainly talk to us or even mention it here, you know, if we have more time. All right.
Thank you.